I just want to highlight two really salient points he raised in that. Number one, energy codes are both political and technical documents. Like, he mentioned that the notion that policy changes in government can affect this. I've never heard a politician stand up at a meeting and go, you know what, I'm not concerned with saving people's lives. I've just never heard that at a political rally yet. But you will hear someone say energy conservation is important, or fossil fuels reduction use is important, or it's not important. And that means whenever you talk about energy efficiency, you're automatically talking about politics and how that plays out in the building community. The second part of it, obviously, it's a technical document. So things like training codes officers to be able to use a document like NECB are important. It's a highly technical document. It's as technical as the rest of the building code, which means, yeah, you need training and you need familiarization to make it efficient and effective to implement. The last part is, when Elric said delays, it cost. Part of, and this is actually really apropos for what we're talking about today, because a lot of the energy code implementation, again, energy efficiency costs money. There is no way to see it. I don't know if anybody was familiar with the old LEED, it's still around, but the LEED rating system used to always have this kind of weird analogy for costing of buildings. And it would say, oh, the LEED building is 1% to 3% more expensive. What they actually wanted to say was, it's 1% to 3% more expensive if you take money out of fit and finishes and put it into energy efficiency. That's not the same building. If I build an identical building, one that is energy efficient, one that is not, I guarantee the energy efficient one is going to be more expensive, and not inconsequentially more expensive. Now, that doesn't mean the economics aren't there. It means you have to put them in a different box. And so a lot of what we'll talk about today, and I see a couple of people from yesterday, we'll kind of rehash in a slightly different way a lot of the legislative background that we covered yesterday, because it pertains, but in NECB, it's even more heightened. So we'll explore that a little bit more deeply, because one of the things that changes substantially in going from a 936 building to an NECB building is the amount of variability. 936 applies to housing in small buildings, and I can go to 99% of the walls being constructed on a residential building in Calgary today, and if I took a chainsaw through them, they're going to look roughly the same. Yeah, the cladding might change, they might use a slightly different house wrap, but the guts of the wall are 99% the same. I cannot say that about commercial buildings. If I go to a downtown office building that's curtain wall construction, its skin of the building is entirely different than how I construct a warehouse. And it's entirely different on how you construct a hospital, to be quite frank. And so when you're dealing with NECB buildings, you are dealing with more substantive projects in terms of size and complexity. You're also dealing with a lot more building types. And so, as I said, while we'll cover a little bit of the same stuff we did yesterday with buildings and use and the legalities, we'll kind of up the ante a bit to go to NECB because, well, frankly, we kind of have to. With that said, I guess yesterday I forgot to do it. I'm Justin. So I actually worked with Ulrich for about 15 years at the city of Calgary. Helped write the energy codes. Before that, I was a consultant. Did some buildings I was pretty proud of. Did some buildings I was less proud of course, like everybody else in their career. But the last few years, I've actually been doing SAIT and some contract work, largely around energy codes. But in addition to all of that, I guess this is what gives me at least a little bit of, I won't say authority, a little bit of street cred in talking about energy codes, is I did help write them. So I was on the Standing Committee for Housing and Small Buildings at the national level for 936. And more importantly, I was on the Standing Committee for Energy Efficiency at the federal level for NECB, and remain on it has a new name, the Climate Mitigation Action. Ulrich, you know it better than I do, but Ulrich's on the one for accessibility, in case you're wondering. Single escape, egress. But the federal committees are the groups that essentially vet all of the technical requirements. And so, again, you have a large group of experts kind of trying to refine these ideas, and sometimes successfully and sometimes a little less successfully. And I think we'll cover both of those aspects today, because, I think at the end of the day, when you're looking at codes in general and energy codes in particular, you're kind of dealing with a 95% solution. you cannot write a single document that covers 100% of the building options that are out there. That is unfeasible. So what you do is you learn what's in the code, and then you have the tools within the code to apply it to those circumstances that don't fit the code. And that's important because that's, again, part of the understanding for all of this is, again, I think that it's really critical to not only understand the what, the where, the when, and the how of a code, but most importantly, that why question. And so we'll tackle just a little bit about that today as well. So hopefully it'll be a good introductory session. I'm not going to call this a compliance session in its full kind of vetting. We have different sessions on how to comply. This is really the kind of, let's put this in the right box session. So it's great for introduction, and hopefully we can elevate the discussion a little bit higher than we typically talk about codes, which is, going beyond the technical requirements, let's say that. So some things we'll do today. We're going to apply building energy flow mechanics of buildings. We're going to identify relevant NECB sections, etc. And we're going to understand the new tiered energy code system. I'm not going to bore you with this, but I will say a couple things that are really important to me is the second point. Understanding the legislative framework of these documents and how buildings actually use energy and why codes are a great start. And once you understand how they work, you should be able to apply them to a much broader set of circumstances. The CEF project is the Codes Accelerator Fund project, was something set up by, was a program offered by Enercan, and there's a large number of interested parties that's being covered in Alberta doing that work. But essentially is to help prepare industry for tiered codes. Tiered codes, we'll get to what exactly that means specifically in a bit. But the realization that never has the code broadcast where it's going before. The codes were written and they're technical documents. So you would get them and you learn to adapt, and we would have 6 months to kind of effectively change our ways as an industry, and that's where you go. Well, the energy codes, I have everything in the energy codes today of what I need to go to a net zero ready, energy ready building tomorrow. We've never done that. We've never broadcast this idea of having different performance levels for buildings and putting them in legislative documents at the start. That's a really good, it's two things. Number one, it's a very good way to prepare industry. Number two, it does tell you where the code's headed. And that's important, again, from a policy perspective and an industry meeting the challenge. Calgary's climate commitment. I'm not a politician. I'm not going to delve deep into the merits or lack thereof of Calgary's climate plan. I will say it is Calgary declared a climate emergency. We have obligations. We have a greenhouse gas mitigation plan. We'll talk a little bit about that. We'll have adaptation plans. They're important documents. They're massive policy statements that say, again, not where we are today, but where we would like to be in the future. Let's start getting into the actual guts of this. Let's talk about the challenge here. We Alberta in general, let's be macrocosmic for a moment. Alberta has a bit of an image crisis. Like, we have one of the highest greenhouse gas emissions on the planet. We have heavy industries that are based in fossil fuels. We have a famously kind of dirty grid, which means we burn a lot of fossil fuels to produce electricity. We live in a cold climate. Those three things in combination are a recipe to use a lot of energy and produce a lot of greenhouse gas emissions. As an indicator of how that goes, these are from the Calgary Climate Change Adaptation Reports. But I just want to point out that non-residential buildings are about 40%, residential buildings about a quarter. Between the two of them, that's about 2/3 of your greenhouse gas. So when everybody says, like, oh, it's diesels that are the problem, and we have to convert diesel buses, yeah, that's wonderful. But you're not going to solve the problem by converting buses to natural gas in Calgary. We have a building problem. And we're a growing city, a rapidly growing city, which means the problem's getting worse every day, not better, typically speaking. Here's the one that I really enjoy. So this will take a few seconds on, and this is, if you ever wanted the snapshot that says why we needed an energy code, it's this one. So I'll explain this. The vertical axis on this graph is energy use intensity. And energy use intensity is simply the expected amount of energy consumption per square meter of building per year. So the higher the number, the more energy intensive it is. While the number is related to use, you just measure it the same way, whether it's a hospital or a warehouse. And typically speaking, the average large commercial building is going to be somewhere between 250 to 500 equivalent gigajoules per square meter per year, as you can see here. The groupings are the geographic areas of Canada. And then Canada as a whole, aggregated here. The colors are the year of construction of the building. So if we look at Canada's data, a building constructed prior to 1920 uses slightly less energy than a building we constructed last year. In 100 years of quote-unquote improvement, we got 7% worse. And I always like to draw analogies to other industries. But imagine if you worked in aerospace. Okay, in 1903, the Wright brothers flew 120 yards on the beach in Kitty Hawk, North Carolina. In 1968, Apollo 8 orbited the moon. That's an industry that knows how to get better at what it does. We demonstrated a negative 7% improvement in a century of trying. Now, there are a lot of reasons for that. I'm not going to, it's overly simplistic to simply say, oh, we're just terrible at it. I mean, buildings got more complicated. We have more electrification. We are way less tolerant of temperature swings on the indoors. We want better views and more glass. Lots of things contribute to it. But the hard numbers are we really didn't do any better last year than we did a century ago. And this is effectively what the government saw. The federal government said, all right, it's time for Canada to put in place an energy code. And that really is what spurred the whole notion that said, if we're going to fix this, we better start regulating. Obviously, we didn't get there just by hopes and wishes. So the unicorns and rainbows methodology of building improvement is not as effective as we once thought it was. So if I was to sum it up just kind of flippantly, we have a large number of underperforming buildings, a greenhouse gas and image problem, and no comprehensive set of tools or guidelines to fix it. Well, I think we actually do. And it's just how we start applying them. And we're going to cover a few things on here. So we're going to start with a discussion on the city charters, which is a funny place to start talking about code, is you talk about a piece of legislation that doesn't even mention code, but it sets a framework. The second thing I think we have to talk about is incentive opportunities. And that is intimately linked to our friend, the city charter. Tiered energy codes are a great way of measuring things. We'll cover why that is as a technical document. And the last thing is the economic pressures of all of this. So if I don't pay a carbon tax or whatever we want to call it, a cap trade, whatever system you prefer, but if you don't put a value on carbon emissions or greenhouse gas emissions, I have very little incentive to move forward. In the last few years, we have seen the op costs of buildings effectively double. Their operational costs for commercial properties are now often larger than the lease rates, which is almost unprecedented. And we have a value on carbon emissions. That means you stop making decisions based on your morality at that, and your accountant starts making the decision for you because it becomes an economics proposition. And again, on a single family residence, yes, those same factors push in. But to tell me I'm going to save $11 a month on my gas bill isn't much of a motivator. But if I run a 1 million square foot warehouse and my monthly gas bill is $247,000, I'm probably a lot more receptive to your argument when you talk about economics at that point. And NECB is what governs that larger building. So let's break this down into the parts, because again, I think it's important if you have all of these prima facie, perhaps unrelated topics, we need to kind of draw some links for everyone. So let's start with that charter document. And the charter document basically says two things that are, I think, really important. Let me back up one step before I get carried away. The city charter applies to Calgary and everything. So I should give you a bit of its history. Essentially, for years, in the province of Alberta, every municipality was governed by the Municipal Government Act. But every municipality meant if you had 200 people or 200,000 people, you followed the same rules. You had the same responsibilities. About a decade ago, the larger cities started saying, well, wait a second. I have a million and a half people. I have a transit system I have to run. I have waste collection that I have to worry about. I have greenhouse gas emissions and smog issues we just don't have in smaller cities. How do I get that? How do I get credit for that? And so they sat down with the province and the city of Calgary and the city of Edmonton, and they essentially wrote a tripartite agreement. And it's the City Charters Act. And it's not out of step with what you would see in any other province, to be honest with you. There's, for instance, in Ontario, there's the City of Toronto Act. It literally recognizes that Toronto is a unique entity because it's almost a third of Ontario's population when you take Greater Toronto. So, like, it's probably not reasonable to expect Toronto and Peel to follow the same rules, and that's fine. Let's recognize that. And Alberta did. So what does that mean? It means we have to have a plan to deal with climate change, and that's adaptation and mitigation. As a reminder, I know some people are going to roll their eyes because they've heard it a million times. Mitigation plans are how you reduce greenhouse gas emissions in the future. Adaptation is how you deal with the effects of them in broad strokes. So you need both. The second thing is not only do I need to write these documents, I have to update them every 5 years. So the recognition that these are not stagnant targets. They will change over time. Economics change, policies change, everything changes. So you have to constantly update and modulate those documents to make sure they make sense. And the last thing, or second last thing, is in black and white. Which is ironically red here, but in black and white in the document, it says that a municipality under the city charter can use environmental factors to judge whether or not a development is appropriate. So that's interesting because when people talk about zoning bylaws, etc., if I have a pure zoning bylaw, all it means is if the building is the right size and the right use, it goes ahead. This actually says, no, I can put in environmental considerations onto that zoning bylaw and use that as part of my evaluation of the development. So what you are building can actually be reflective of the needs of the climate change plan. The last part I got to say, because this is why politics, I have a very hard time in my mind separating energy codes from politics entirely. Originally, it basically said that the larger municipalities could put in place bylaws that would affect energy consumption in building. And we argued with, and I can say we because I was with the city at the time, we argued with the province for about 3 years on that. And the province eventually said, our legal team is telling us the Alberta Building Code is a provincial document. That provincial document sets the tiers. Alberta has one tier, and they ripped it out of the City Charters Act. So I hate to say it, but this is a wonderful case of use it or lose it in a sense. And they took it away from the cities, which is okay, because we'll talk about why that doesn't leave them completely powerless in this scenario, but it's a significant change in the legislative body. So basically, since half a dozen years ago, we've had an obligation to create and update climate change adaptation mitigation plans. We can use environmental objectives to evaluate development. And the last one, which is while we lost the ability to legislate higher tiers, you clearly still have the ability to incentivize higher tiers. And I'll do this. This will be the first of several today, but put a pin in that word of incentivization because it's a big one. Because it's kind of the crux of how municipalities have to operate in this new context. So, if we're going to talk about incentives and we're going to explore this a little more in depth, I have to explain my opinions on how incentives work. And this is not hard and fast science. You'll note there's no numbers on here. But I have in some way, shape, or form been doing energy efficiency in buildings for a quarter of a century. So at least I've got enough tummy rub engineering behind me to say this is probably not entirely wrong. Again, let me explain the graph. Vertical axis, number of projects. So how many of something do I build? That's all it's trying to illustrate. Horizontal axis, some measure of sustainability. For our intents and purposes today, let's call it energy efficiency. What I would say, and I don't think it's an unreasonable supposition, if I took the building stock we constructed in a year, you're going to have a range of projects. So you'll have a large number that are kind of in the middle that say, yeah, we're reasonably sustainable or energy efficient. You'll have a few projects that are very energy efficient, and you'll have the laggards, of course. Groups that are just saying energy efficiency doesn't matter, I don't have the money, whatever it is. The rationale is largely irrelevant. But I think that idea of a normalized distribution is reasonable. Where I think the insight comes in is understanding what they respond to. Because the low end of the sustainability spectrum only responds to legislative change. They are concerned primarily with capital cost expenditures. As I said at the very start, I cannot, if someone ever asks me my opinion and says, I can do energy efficiency for free, I don't know how you do it. I'm sorry. Installation costs money. Better equipment costs money. Like higher efficiency, everything costs money. So if you're only concerned with capital, you really are only looking to do the minimum compliance. On the flip side of that, take the higher end ones. If you exceed code in every way, does a change in code impact your building? This is a really good example. We have to be in one. This building was LEED certified, right? So on paper, it should have beat the NECB by several percent, probably 10 or 15%. So what does a change in code do to this building? Nothing. It's not impacted by the codes. It's already progressed beyond them. What it does respond to is things like incentives, market valuation, opportunities of how to capitalize on projects, policy statements for individual organizations. Like, those are weird things. Those are things that we don't generally consider in a code system. So when I think of this, I look at these as pushes and pulls. And I can say here, if I change the codes, I'm effectively pushing the low end of the market. But I don't move these guys one iota. A changing code doesn't help this person, or this group of consultants and contractors. On the flip side, I can have all of the high-end incentives I want. Heat pump incentives, what else is a good one? You know what, that's a perfect one. Giving me $5,000 for a heat pump on a $20,000 heat pump system versus a $7,000 furnace, if I'm concerned with capital costs, thanks but no thanks. It's not going to hit, it's not going to resonate with me at all. And the same goes for every part of a building. So you have this push-pull situation. And my hypothesis or my supposition would be, if you know where you are today and you want to be farther down that energy efficiency world or something, you need both pushes and pulls. That's how you move the industry. Now, the interesting thing about moving an industry is all of a sudden then the cost modeling becomes very different. I'll give you a really good example. When 936 was implemented, I know versus an NECB, that houses really respond to this well. When the province of Manitoba put in 936, they overrode the code. There was a U-value requirement, but they also said, no, Manitoba's cold. Everybody puts in place triple pane windows. And at first, everybody freaked out and said, well, I can't afford triple pane windows. Go buy a triple pane window in Manitoba today. Costs exactly what a double pane does. Because the entire industry had to change. There was no market to build double pane windows anymore. Think of the catalytic converter on your car. There's a reason people steal them. They've got palladium, rhodium, I can't remember the last one, but extremely exotic and extremely expensive metals in them. The reason you don't notice the cost of a catalytic converter is try to find a car without one today. It doesn't exist. So they've just baked it into the price of the machine. And that's how you change the industry. And I'm going to say it's effectively an equation. So if I have an adaptation mitigation plan, which I'm obligated to do under the city charter. And I have some decently thought out development incentives, and I'm using environmental and charter-based criteria to approve development. And I have a way of verifying the building performance, i.e. the minimums can be maintained and measured well. That's your recipe for better buildings. And it's that simple, in my opinion. We as an industry, construction, often don't get there because we still kind of operate in this lone wolf mentality. And it's part of it is because there's a very low barrier to entry into construction. We can have a whole day-long session on how the construction industry came to be the way it is. But I just got to point something out, which is look at aerospace. Go look at a Boeing product and an Airbus product next time you're on a commercial airliner. The amount of similarity between those designs, you have to have a very, very well-trained eye to tell the difference, because they've understood that we have to work in concert in order to be able to maintain that kind of quality. So with that said, I'm gonna pause there. That's the end of our kind of like incentives, merry-go-round, whatever we want to call it this morning. We're gonna go into the legislative constraints because they're important. But any questions on city charters, incentives? Seeing none, we're gonna keep on going. The legislative body in Alberta pertaining to codes and energy codes in particular is a pyramid, and it's got 3 layers to it. The base level is the provincial authorities. Second level is the Safety Codes Act. The upmost is the Municipal Government Act. You can also look at that tripartite organization in a project development. We'll be doing both. But you essentially have an owner or someone, and that owner can be a city, that owner can be a private individual, that owner can be a trust fund, it doesn't matter. But somebody says, I need to go build a building, and they have dollars to do it. You then go through a development permit process, a DP, which essentially tells me what I am building, and then a building permit process, a BP, which is how I am going to construct that. And in order, that is how you progress every building that is constructed in Alberta. This may get waived by a bylaw check. We'll talk about that, but it's just a modified. What's interesting is in terms of energy efficiency, here's where you set the goals. And we'll talk about why that's important in just a second, because when we talk about incentives, that's the base. The DP sets the broad energy goals and broad energy context. So it determines how tall my building is. What's the shape of it? What's its use? Off the jump, I've set 50% of the energy consumption criteria for that building. Hard numbers. I say that, and I always feel I have to justify it. We did a study some years ago for the National Research Council that talked about energy use intensities for building types. And I always found this really interesting because I was grossly wrong. But the broad kind of summary is in Canada, for most climate zones, when you kind of average it out, we would have energy use intensities from 150 to over 900. Anyone want to guess? This is commercial buildings, in case you were a commercial industrial institution. Anyone want to guess what the 150 was, the 100 level, the lowest? Warehouse. Not surprising. They're not really well ventilated. They don't use a lot of lights. They don't have a lot of demand. I hate to say this, they're kind of big dumb boxes. Offices came in at somewhere in the neighborhood of 350. Residential were between 200 and 300. Hospitals were very high. They came in about 550. Anyone want to guess what the highest one was, by the way? I always find this really interesting. That's a really good guess, Joe. No. Nope. Stand-alone massage restaurants. So the stupid little McDonald's you see on the corner is in Canada the highest energy use building we build. And it's about 900, by the way. It's extremely high. Yeah, bad envelopes, open 24/7, have to have a massive exhaust hood over the cooking services. Doors are constantly opening, lots of glass. Like everything about them makes sense But it's funny how you would take the worst little buildings, the ones we would honestly, in terms of energy policy, wouldn't even think about. But technically, they are the highest energy consumers. We actually did a GIS study. Sorry, I'm getting a little off track, but I find it interesting. The GIS group wanted to do an energy mapping study for Calgary. And so they started off by mapping out all of the airports. They said, well, the airports and hospitals are going to be the highest use. And knowing what I knew about that study, I said, can you do me a favor and just aggregate the fast service restaurants? Crushed the airport and the hospitals. Like they didn't even appear on the map anymore because, yeah, they're small, but they're extremely intense in their energy use, and there's a lot of them. So, just interesting stuff for policy writers. Last part, and here's where the energy codes really come in. The how, the verification. How do you measure this stuff? Measuring energy can't be done by simply grabbing a utility bill, because I always joke about this. I have a 1960s flat roof bungalow that I've done some energy retrofits to. Nothing spectacular. But I also keep it at 17 degrees C. I shower at work because I cycle. I do a lot of things. I am almost in the neighborhood of net zero energy ready, just because of how I operate my building. But if I move out and a family of 5 replaces me, and they have teenagers who decide that 30-minute showers every day is what they need, the energy consumption's off the chart. Same building, just different use patterns. So you really need a smart way to measure this stuff if you're going to do an apples-to-apples comparison. So going back to our pyramid here, let's talk about the provincial authority. So yes, the province sets the energy tiers. Yes, the province controls the energy, the level of energy efficiency. However, the code is extremely clear about something. It's the owner of a building that is ultimately responsible for code compliance. Not the city, not the consultants, the owner. That's a really interesting perspective. And I'll say that because that means if they're responsible for the level of energy efficiency, and we're reminded that codes are floors, not ceilings, like I constantly say, people forget, code, like saying you've met code on a building is saying you've done the bare minimum. Like you might as well say, every time you see code compliance as a marketing tool, you can replace that line with saying, if we did a slightly worse job, it would be illegal, because that's what it actually means. You have to meet the code, but there is nothing preventing an owner from saying, no, my interest is I'm going to elevate the energy performance. As long as you've met code, you can blow it out of the water. That's okay. So how fundamentally, again, here's where you might want to stick a pin in this idea. How do you encourage owners to voluntarily build to a higher standard? Because that's a non-trivial question, especially given that we couldn't, if you recall back to the city charter, we lost the legislative ability to make them do it. So now it's a question of how do you encourage? Going up a step, let's talk about the Safety Codes Act. And the Safety Codes Act is essentially the document that empowers codes. It's why we referred to the City of Calgary as an authority having jurisdiction. It's why we have the Building Code, Alberta edition, as our document. They are substantive impacts, obviously. The Safety Codes Act enables all of the building permit processes we deal with. And there are a lot of ways to do this, but going back to the metrics question, yes, tiers and codes set the minimum standard, but they also give you a lot of tools on how to effectively measure things. And that is particularly true in energy codes, because it provides all the rules I need to make a fair comparison between a couple different building types. So the purpose of it, it sets everything from which document we enforce to the procedures we're going to use to appeals processes. We don't need to spend a lot of time on that, but I just want to point out this guy. When you look at the Safety Codes Act, and its companion document is the Building Regulations Act, it's just a different kind of offshoot. But it lists the documents you have to follow in Alberta. And it lists the National Building Code of Canada, or the National Building Code 2023 Alberta edition, and the National Energy Code of Canada for buildings, the NACP. Note how it doesn't say in addition to or when convenient. It just lists two pieces of legislation you must comply with. So they have not put a hierarchy on any of this. That is an intent in law. When you list 5 things and you don't put a hierarchy, you have to meet all 5 all the time. That's what that is saying. If they didn't want that to happen, there would have been a massive or they would have numbered them in a different way that says, no, this is subservient to this. They didn't do that. So you have to follow both of those codes all the time, which means you're always obligated to use the most stringent model of that. The other thing it did is it established us as a Tier 1 province. So basic code compliance. Now, what's interesting about that, again, think back to what I said. The tiers are already built in the code. So for Alberta to become a Tier 2 province, I only have to change one sub-article. That was on purpose. They've done that to enable provinces to rapidly implement higher levels of code compliance. It's not an ill thought out system. We might be cumbersome, but it's well conceived in its use. Within the Safety Codes Act, there's a bunch of things, and you can ignore 99% of them. This is the one we can't ignore today. Legislative hierarchy. So I just said that the Safety Codes Act and the building regulations do not have a hierarchy between safety codes and energy codes. But there is a legislative hierarchy, and that comes into place when we talk about the municipal government. The Municipal Government Act, in short, is the document that controls all of the development requirements in Alberta and Calgary. It's like, it is also sitting above, if we go back to this guy, it sits above the Safety Codes Act. Because what the Municipal Government Act does, yes, it enables development permits, but it also basically says it's the document that gives a city or a municipality the ability to produce bylaws. So if you want to enact a law, you are referencing somehow the Municipal Government Act. And I can put in place any kind of bylaw I want in Alberta until I get to one very critical point, and that is Section 66 of the Safety Codes Act. The reason we have to put the Municipal Government Act on top of the Safety Codes Act is it says, if I am putting in place a bylaw that addresses building construction, it is inoperative. It is not a law. I can write it, but I cannot enforce it. Why is that important? So I will explain why it came to be before anything else. It is there as a way to ensure minimum code compliance for safety. That's where its roots are from. So what they didn't want is some economics officer in a small town saying, hey, I want to attract housing development. We're not going to enforce code. Because the minute they said we're not going to enforce the building code, everybody could take them to court and say, no, that's an inoperative law. You can't do that. What it has also meant, though, is the kind of devil's in the details component is it also says I can't put in place things that address the construction of a building in bylaw. So that is not the same as saying, as an owner, I set different standards. That is me as a city saying, if you want to build here, you must build to a different standard. I know that sounds like a subtle difference, but it's effectively saying, I can control what my house looks like. I can't control what my neighbor's house looks like. That's a really coarse analogy, but it's not super inaccurate. So if we've said that bylaws that affect construction of a building are inoperative, what are not inoperative under the Safety Codes Act? There's a lot. Zoning of a building is not its construction. It is what its use is. Setbacks, building heights or floor area ratio, site coverage. And the big one for me, incentives. There's a big difference in writing a law that says you must do something versus I'm going to put in place a program that enables you to do this. legislatively speaking. One is a law, the other is a program. They're not the same family of decisions. So let's talk about what we can do on that. And it goes right back to this question. I asked you to put a pin in this for a reason. If part of the understanding is an owner can exceed code anytime they want, and that includes energy efficiency with respect to energy codes, and it's voluntary, then how do I incentivize them correctly? That is a really foundational question. And it's a non-trivial question, because think about something as simple as, we had a roofing rebate program in Calgary after a hailstorm. We said, we're going to give money for people to put on hail-resistant shingles. We went through several $1 million in a week and a half. I think it was somebody, Lizzie, you'd probably know the number better than I, but it was a very short order where we managed to spend that entire fund. To great effect, I think. But the point being, these cost money. So if you can build a smart incentive program, you can encourage people to do things. Now, I don't want to go through this in a lot of detail, because that's kind of why the papers are on your desk. But I will say that there's everything from fast-tracking permits, so recognizing that time is money on a project, to SAIT programs, which is basically giving money leaned against the building's property tax as a loan for renewable energy systems, to municipal government incentives, bonus density. All of those things are all incentives that are available, a lot of which have been put in place in the larger cities, but all aimed at the idea of how you build a very simple idea, which is, if the objective is to reduce greenhouse gas emissions in Calgary, and energy code compliance at a higher level is one of the ways to do that, what's the guts in between the two that get you there? And that is an absolutely non-trivial question. We have, I think, I want to say the climate group at the city of Calgary is up to like 25 people who job 2,080 hours out of the year for 25 people is to figure this out. So there's a reality to it. What do you do to get there? Again, I'm going to pause just briefly for a question if anybody has any, but I'm going to ask you also to put a pin in that chart and think about that whole idea, how you go from, if our goal is to use less energy and our way to do that is better buildings, what's the guts in between? And I don't see any question. In order to do this, I think you have to understand energy use of buildings. And again, I'm a foundational believer in explaining why things work, because then things like code articles, you take all the mystery out of them. It's obvious why they're there once you understand building energy use. So concepts. What impacts energy consumption? What systems affect energy consumption? It's not the same question. We're going to spend some time on this, because this is where NACB swings wildly from 936 buildings. So I'm going to start with this one, because I just want to draw a very obvious thing. So I'll explain what this is. These are snapshots from a study that got done for the National Research Council on energy modeling in NACB. So they're the best, to our estimate, the best, most properly done energy models you could get your hands on. This is modeling a warehouse building in different climate zones in Canada. So everything from zone 5 up to zone 8. Different colors are what the energy use went to. So the teal color is area light. The light green is equipment. The orange is ventilation, and the green is space heating. So first thing I want to say, two things that I think are critically important. You'll notice how some of those change with climate and some do not. Not surprisingly, the colder the climate zone, the more you're going to use for space heating. To the point of, if you are in, this is us, this is zone 7A, you're looking about, eyeballing it, 92% of the energy goes to space heating in a warehouse. So if I want to fix warehousing, I better understand that. Because an incentive on air conditioning for warehousing I'm not going to have a lot of takers. I'm pretty much, I might as well put the money in a fund and give it away. So that's how energy use gets used within one building. This is the other part of that compendium study, which says, let's look at different kinds of buildings. And again, what you will notice is, and it's the same idea, dark green is space heating, some of the big ones, miscellaneous equipment, process loads, etc. Rejected heat comes in on some of them. Ventilation is a big component. The energy use of different kinds of buildings is all over the map. In order to set up incentives well, that is very fundamental. Because if I'm going to give somebody $100,000 and I want a greenhouse gas emissions reduction, coming up with the greatest incentive for hot water tanks on commercial buildings, probably not the use. Just not the best use of my money. But you need to understand, if you don't understand that, you are going to guess wrong. And that's part of where we have, I'll be very blunt, failures in policy is when we don't understand that. So let's look at energy flow within a building. So these are called Sankey diagrams. And I always say this because I wish I would have come up with these. They're basically energy flow maps. And the lines show what's being connected, and the width of the line is how much of something is. So the fatter the line, the more energy, and then it's simply, this is going to this. Now, not surprisingly, this is the Sankey diagram for a commercial building in the northeastern United States in winter. Okay, so it's kind of peak energy use in a climate not dissimilar to ours. And you'll see everything from your equipment uses some, lighting, the boilers. But just look at that. And again, think back to the last drawing we were just talking about, where energy goes. You got one problem to solve. It really can't be more blunt than that. This line is natural gas going to a boiler, lost in the thermal envelope, and the various components that take it up. So that is literally just parts 3 and part 5 of the energy code. But it's also 3/4 of the energy problem for that building. So that's all it is. If you understand that, you can write policy that positively affect a building. And when you need to enforce an energy code, you understand what parts I should be dedicating my time to, because that's the guts of it. Again, if I go back a couple, this is the drain waste heat recovery for a commercial building. Now, if it was a rec center, it's a totally different line. I fully understand that. But in a commercial building, asking somebody to sink thousands of dollars into a waste heat recovery system for the domestic to solve 1% of the energy problem, if I could operate at 40% efficiency, I get 0.52% of my energy reduction. You know how else I can get 0.52%? Hey, Mary, can you turn off the lights in the meeting room? Because that's about the same amount of energy you're talking about in these kinds of projects. But that's what I mean. You have to ground this stuff in the reality of buildings. And to do that, we have to understand a few things. So number one, heat flows from hot to cold. Everybody understands that. What slightly less people understand is the modes of heat loss. And that's important because they're not all the same and the code doesn't treat them the same. We basically have 4. Conduction, heat flow through a solid. Convection, looping within fluid systems. Fluids can be air or water. Advection is the carrying of heat through the loss of mass. And the simple analogy I would draw is if I'm carrying a bucket of hot water outside of a building, I haven't just carried water, I've carried heat. So buildings don't lose water. I guess they do through the drain waste systems, but that's one small example. But what they do lose a lot of is warm air. So this is essentially your air leakage value, and then radiation is the emissions through the infrared part of the spectrum. Those might sound like very abstract terms, but I want to ground this in reality because a window does all 4. And we don't think about it that way, but it absolutely does. I've got conductive heat loss through the frames, the sash, and the glass itself. They're solids, and they all lose heat. I space this glass a fixed amount for a reason. I don't want convective currents forming within a window. If you ever look at a window, like, go humor yourself one day. Find any double pane window, I guarantee it's going to be between 10 and 12 millimeters apart, because that's the optimum distance where the thermal losses from heat flow through the air and the pinching it enough so you don't get convective currents is optimized. The draft you feel next to a window is often a convective current. I have radiation through the glass itself. Whenever you see low E windows, nobody asks what that E stands for. That E stands for emissivity, which is just a numeric value of how much of the radiation spectrum that thing will emit. So by having low emissions, you are cutting down the radiation heat loss through the glass. That's what low E literally says. And the last one is, of course, advection, which is depending on how well the window was installed, how well the weather stripping works, I'm going to lose air through that window. So one simple window, all four mechanisms of heat loss. Now, what I need to point out, the energy code really focuses on two of them in spades. Conductive heat loss, so that's your U and R values, and advection, which is the loss of air. Those are the two parts that the energy code is really, really focused on. Just a brief reminder, you can read these at your leisure. U is thermal transmittance. Basically, the smaller the number, the better it is at keeping heat. U value is related to something called R value, is the inverse. R is thermal resistance. U is thermal transmissivity, not surprisingly. If I increase the resistance, I have less heat loss. If I increase the transmissivity, I have less heat. So, I'm going to ask you to invite my colleague up because I'm getting old and I need a break from my voice. But Hussein's going to walk you through a few questions because, to me, we call this a workshop, which means I don't want to just talk for 2.5 hours. I'd like to hear your feedback because we've covered some pretty broad range topics today. Everything from civic policy to government legislation to literally first year physics on how this stuff works. I would like to hear your thoughts on what that means because we have to, part of the CAF project in general is getting municipalities and industry ready for higher codes. So here's an opportunity for you to give us a little bit of your insights on how we can do that most effectively. Because I don't do this stuff very often anymore. So I might know the theory behind the code, but I certainly don't implement it. So I'm going to ask Hussein to, we're going to do a rapid run through the NECB technical because again, I want to reinforce the idea that the energy codes are political documents and technical documents. I think you need to know both. To be very frank, to apply them in a smart way. We're going to break this down by, obviously there's changes through parts 1 through 8. We'll talk about those. And our good friend tiered code, which in the energy code world, or NECB world, extremely straightforward. So we can rest assured on that. Brief reminder, I think it's important to understand how the energy code is broken down. So it basically chunks out the building into systems. So you have building envelope, lighting, that's interior and exterior, HVAC, heating, ventilation, air conditioning. If anybody hasn't seen that, I'm sure you'll have. Surface water heating, which is all the hot water needs in a building. Electrical systems and motors. This is utterly useless. I love picking on this section. Part 8 is a big one. It's where you talk about all of the rules for performance modeling. And that is, quite honestly, from our experience in the city of Calgary, 99% of NECB submissions are performance modeled for a reason. It's the right way to use that document, to be quite frank with you. And then the new one, our good friend Part 10, which is the tiered energy codes. Again, a reminder, you do have a few compliance paths. So for anybody who's used it, this is old hat. I apologize, but I just want to walk through it quickly. Prescriptive path, parts 3 through 7. Prescriptive means you simply do what the code says. So an example, this is the maximum permissible U value for a window. Show me that the window you've installed meets that U value. That's all you have to do. You have to follow that and go, okay, I followed the rules, check on off. You have to check off all parts 3 through 7. Trade-off means within a system, I'm going to have certain components that are above code performance, certain components that are below code performance. Trade-off means mathematically, I can show you that overall, I have not made the performance worse. So it enables you to kind of violate prescriptive codes, but at the same time recognizing you have to make up that difference within that system somewhere else. Performance path is the one that says effectively all bets are off. I'm going to tell you to run, you're going to tell me you're using performance path, which means you run an energy simulation. And if your building that is constructed according to the rules of Part 8 can demonstrate that it uses less energy over the course of a year than the prescriptive version of it would have used, you're good to go. So what's nice about that one, that's the one that enables me to do trade-offs between systems. So instead of having to trade window for window as I would in a Part 3 trade-off, I can now trade off envelope performance for mechanic performance or lighting performance, all of the above. And that gives a lot of flexibility in your design. And it's literally why when you think back to all of those things we talked about the energy consumption in buildings and how all over the map they were, that is why almost all competent NECB applications use performance bond, because it lets me take advantage of all of those weird little bits and nuances to a building. So it is logically consistent. It also means it's great because you can really focus your time and energy on one of the compliance paths. This is right out of the code, and I just want to point something out. I don't know if this has a pointer, but I don't know if you can read it. This is a very complicated chart. It's funny, I sometimes blank out everything after the first line because it's only the first line that matters. And the first line says this: as an applicant, you have to do prescriptive or trade-off or performance compliance. You can't do both. That's what that line says. Select compliance option. Great. But that's the most important part. Everything after that is just really the minutiae of the process. But the really critical choice is you have to state unequivocally, I'm doing a performance model or I am doing prescriptive or prescriptive trade-off. Once you've made that choice, all the path. Let's go to building envelope for just 1 second. There's a couple salient features that have changed. A few small ones, a few big ones. Updates to the air leakage is the big one. So let's talk about this. So when we have understanding something fundamental, anybody who was here for 936 yesterday, so that's housing in small buildings, one of the things we said, there's no fenestration door wall ratio. Okay, there's guidance on how you model it, but there's no requirements. NECB does the exact opposite. It very quickly recognized that says, I've allowed 10 times the thermal transmittance of a window to a wall. So you're going to tell me, humor, pretend this is a window, this is a wall. You're going to tell me the ratio of these. I'm going to put limits on it prescriptively. That's a really big step. And it's a big step for one simple reason. Now, the design of the building plays a critical feature to that. I can now, as a designer, if I know what I'm doing, I can actually change fenestration ratios to improve or decrease energy efficiency and help that as a code compliance model. That's why I often refer to NECB as the ultimate consultant's code. If you're a smart consultant, having said that energy efficiency costs money, the proviso of that was on an identical building, right? If I'm a smart consultant, I can actually say, no, you know what? This window can get cut in half and I can decrease its performance accordingly. I could save money on a building, weirdly enough, if I know what I'm doing. That makes it a consultant's code. The other thing is air leakage It's very much a tested feature. So let's talk about this fenestration door wall rate for just 1 second. It's formula. I'm not going to walk through the formula, but it basically says in Canada, the colder it gets, the less window you should put on your building because they are so much more thermally conductive. And this is the ratio. Just happen to say, Calgary happens to be exactly 5,000 heating degree days. We are 33%. So any building prescriptively can have up to 33% glass. And if I use less than 33%, I can do a trade-off calculation to decrease its performance or adjust the other walls accordingly. So you can see how all of a sudden the choices you make in a design in NECB world are significantly more impactful than they are in a 936 world. It's also interesting because if you read things like area redevelopment plans for the city of Calgary, I happened to look at one not too long ago, but it was a 16th Avenue plan that said, we would like to see 70% glazing between, I think it was 0.6 meters and 3 meters on main floors. Okay, that's a policy decision. But that is a policy decision that directly impacts my energy performance. And again, how interrelated the idea of policy documents and energy codes really are on especially complicated buildings. I just included this to reinforce the difference. These are the U values for the opaque sections of wall. These are the U values for the transparent sections, the fenestration. You will note, for us, it goes from 1.73 to 0.215. That is 8 times more thermally conductive to heat. That fenestration door wall ratio number is a big number in NECB because of that. Like, air leakage, if you want the whole lowdown on all of the permutations and combinations of air leakage, when we do our compliance session, go to that one. We're going to cover this very briefly today. I just want to say there's basically 2 ways to comply in NECB, and that's new. So in the old version of NECB, everything was based on the materials. That's an S741 standard. And the other one was an assembly standard. That was the S742 standard. Okay? What did those tell me? The material standard said I have to have a material that's an air barrier. Everything's an air barrier. Paper is an air barrier. Glass is an air barrier. Drywall is an air barrier. What a 742 test tells me is what's the air leakage at the transition of those things. So it's an assembly test. Both of those are helpful. However, neither of them actually tells me the quality of the installation. Because a 742 test, so yes, the manufacturer of that product will send it to a lab and test it. That assembly was put together by their best technicians in a perfectly controlled, a climate-controlled warehouse by people who know what they're doing and have time to do it right. Is that what you're going to see on site? Maybe. So the new one talks about, next slide, yes. I can also now do air barrier testing building. So that is huge for 2 reasons. Number one, that is how you know it was installed in reality correctly. It's by doing an air leakage test. And number 2, because I now have a whole building air leakage metric, I can model against it in the performance compliance path. So in the good old days, when we started doing NECB, one of the big shortcomings, in my opinion, was you could not use air leakage in your performance model. So you basically built the building, you could play with the modeling of the mechanicals, you could play with the modeling of the windows, the solar heat gain, all those things. And then air leakage was just assumed to be the same. Now, because I can test against the building, I can actually say, no. I'm going to model mine at half the air leakage rate of the reference building. Where does the complexity come in? You are modeling something I have not yet built. And now I go test it in reality. What happens if it doesn't meet those requirements? I don't know. I'm not exaggerating when I say I literally don't know because no one's got there yet. but somebody's going to have to figure it out, because if I was doing a building right now, especially if I was doing a very complicated hospital or something, I know I'd be modeling that leakage down.
Heard that the designers, the architects, they saving this modeling, and then they say these higher, better performance thing. A contractor has to come in and actually make it happen.
Yeah.
So, how are we actually ever going to resolve that? Because someone else has to take over someone's promises.
So that is a great question. Like, think for the liability. You said it perfectly. You're taking over someone else's promises. Think about litigation in construction. Just think about that for 2 minutes. Nobody sues a builder. Like, I used this example yesterday, and it's completely apropos. I built a building, and 3 years later, the roof leaks. I don't know if did the roof membrane fail? Did the person installing it fail? Did the mechanical contractor who was installing the flashing fail and step on a bunch of fasteners? Did somebody do vandalism after the date? So what happens is, you have a leaky roof, you sue everybody. That is literally what you do. You put the list together of all the people you're going to sue for that. And now that's in the case of failure. But now you're talking about something that says, we modeled the whole building on somebody adequately installing an air barrier. What if they fail? And let's be very honest, any of the contractors I think will agree with this. The person installing the air barrier, typically the lowest paid and least trained person on site. It's usually the laborer who gets the lousiest job, because it is a lousy job to install air barriers. That's a pretty big commitment for a $100 million building if you give it to the lowest paid guy or girl. Anyway, that's your takeaway. The legalities, we could do that's a whole different discussion. That's where we get people who actually make real money, like lawyers involved. You still do have this option. You can't still just do the assembly tests, which is fine. All well and good. That's what we've had in place for years. But on an assembly test, cannot put that into lighting. Lighting is really, in all honesty, if lighting is the easiest chapter to sum up, because it's basically 3 things, and I'm not exaggerating. How much wattage did you put into the light? How do you make sure that the lights get turned off without somebody following everybody around and manually turning off the lights? And how do you account for daylight? That is all that it does. And it's literally the entirety of the lighting chapter is basically, how do you calculate lighting loads, and how do you make sure they get turned off without somebody doing it? It does cover interior and exterior, obviously, exempts things like emergency lighting, because, again, code writers may not be the greatest people, but they're not insane. They understand that in the time of an emergency, I'm probably not worried about the lighting consumption. There are 2 methodologies available to everyone. Come back for compliance. We'll talk about those in great detail, but I really just wanted to show that there's a building area methodology. Essentially, if you're single-purpose building, you can use the area of the building to establish it. The other one is you break it up into the actual spaces. These are the tables that govern. I do want to point something out, because it does come in. There are lighting power densities, and there's also tables. I think we have it on here. Yeah. You must understand the daylighting and the controls, because daylighting, you used to be able to ignore it in NECB models. I didn't have to include. I could just say, you know what, I'm lazy, but I'll take the 5% energy penalty, model without it, which in a lot of cases made sense. Warehouse is a good example. Again, can't do that anymore. You must now take into account daylight. It's funny, because as I pointed out to my colleagues on the standing committees, I have no control over on a building code, I have no control over what happens across the street. So how do I know I'm going to get daylighting in a building? I don't. It's a very odd thing where we made you account for something that in reality may or may not be there. HVAC systems. I'm going to let you read this. I'll give you my personal opinion on HVAC. There's an almost easy recipe to comply with NECB. and it's you trade HVAC performance off of envelope, because the envelope requirements are very stringent and the HVAC requirements look like they were written in the late 80s. Like, it's pretty straightforward stuff. Like, that equipment is not hard to get. An 85% efficient boiler, yeah, that's not tricky. A COP of 2.9 on a heat pump, I could have bought that from Germany in the early 80s. Like, they're really kind of antiquated standards, for better or for worse. But just a couple things. One of the ones that is important, I think, is the realization that, again, all the emergency systems are exempted from it for good reason. And the one that I want to talk about is energy recovery. And energy recovery has made a significant leap forward. And part of it was there was a lot of what I would have considered ill-considered wording in the original editions of NACB. And it left a lot of questions when you had to put heat recovery on a building. And again, depending on your building type and your climate, you can have a lot of combinations to a mechanical system. So I'll give you a good example. We measured everything in the original NECB on exhaust, like CFM of exhaust, right? What happens when you had paint hood? So I would have something that, when it was not in operation, would ventilate at a few hundred CFM. Literally, it's a warehouse. But the minute somebody clicks on that fuel hood, the exhaust rate goes 20 times what it was. How do you account for that in a model? You can't just tell somebody, well, we're going to assume you leave it on 24/7. That's nonsense. You can't ignore it because it's a big part of the energy consumption. So what they tried to do is be a little bit more specific. So they said there's 4 criteria. Does the system operate continuously or non-continuously? And for the NECB, that's 8 hours a day. So if it's more than 8 hours a day, we have to continue the system. How cold is it outside? Obviously, if you're measuring this on the amount of air you're bringing in, if I'm bringing in minus 30 air or plus 20 degree air, that's a big difference. How much exhaust air am I producing? Again, the volume question. And the other one was mixing, which is how much of this air is being recirculated. And when you're doing mechanical design, these are all questions that need to be answered. Like, that's important stuff. So what they did is they basically made a couple tables. And I'm not going to bore you with the details, but basically a certain amount of outside air when it's cold enough and a certain amount of flow rate, you must put on heat recovery. And if it's NR, stop. So this is for the non-continuously operating. This is for the continuously operating, which basically says unless you are operating in either the southern tip of Ontario or the lower mainland in BC, you're going to be doing heat recovery. So it's a lot more accurate than it was, which is good. It added a little bit of specificity and took a lot of the ambiguity out of it. There's, I think, 12 pages of tables on equipment efficiencies. All works the same way. Find your size, find your fuel source, figure out the efficiencies, model it from there. Xera's hot water works almost exactly the same as that. They have taken off, I should say, this is worth noting, in NACB 2020, there is no trade-off path for mechanical systems. So either HVAC or service hot water. So you used to be able to do this weird, it was effectively arithmetic gymnastics. Because if you remember your junior high algebra classes, if you have more variables than you do equations, you have literally an infinite number of solutions to that problem. Yeah, newsflash. You had more variables than you had equations to solve the HVAC one. So they generated a bunch of tables that were kind of focus and nobody used them anyway because it was a pain, so they just turfed them. So that is one of the rare cases where you get to put Saint Exupéry's famous quote, which is, perfection is attained not when nothing more may be added, but when nothing more may be taken away. So they took away the trade-off paths. Firefighting systems exempted. Part 7, I keep that in there just because it's such a joke chapter. I encourage you to read it because it's like a page and a half long. Apart from monitoring systems, I've never had anybody ask a question about it because I don't know if anybody cares. Go ahead.
System updates. just the other west slide, right? Sorry, too many. Wonderful, it's very update to water heating equipment efficiency.
Yes. So if you look at again, not didn't include them in this presentation, but if you look at in part 6 of the NECB, a whole series of tables, and they did change some of the efficiencies. So they made them a little bit more. So it's everything from, again, I think it's about 4 or 5 pages worth of tables, but helpful hint. If you're ever reading code, there's a short. Look at the margins. You'll see vertical lines, and that tells you where there's a change. I don't know why no one tells everybody that when they're looking at a code, but it's like the best shorthand ever, and nobody follows it because nobody knows what it is. But just look at those tables, and if you see the vertical line, that's it. Performance compliance. Again, this is 90. Makeup some time, so I've never actually done that, but it's high 90s. This is the compliance choice for everyone, because it makes sense. That's the only way to describe it. It's almost like you're kind of crazy if you don't do this, but it does mean a couple things. You have to know about the building, because again, all of those things, like the different amounts of energy that go into different uses, use is important, size is important, makeup of the material is important, mechanical systems are important. Now, I can't walk into a performance modeling and say, go make it up on site. It's really interesting. Again, part of the reason I like NECB much more, find it much more interesting than 936. When I call it a consultancy code, that's what NECB demands you do. It means you have to kind of finish the design ahead of construction, which I'm gonna quote Wolfgang. What's his name? His last name escapes. Wolfgang something, but he was the CEO of Siemens, that little firm. He gave a presentation at a BIM conference I was at. His words stuck with me because he basically talked about performance of construction as an industry. But why don't we build? Why do 12 people can build a car now when it used to take 200, and yet it takes 200 people to build a building 20 years ago and 200 people to build it today? And he pointed out something I'd never thought of. It was construction is unique. It's the only major industry that insists on starting the fabrication before finishing the design. And I was like, Jiminy Crickets, he's right. You would not start a $20 toaster assembly line without knowing every part of that toaster and how it's going to fit together. And yet we will literally routinely start digging a hole on a $200 million building with the vague conception of what the 30th floor looks like. That is insane when you think about it. But it is the nature of the beast. It's what happens when it takes 3 years to construct something. Again, well, let's all meet again in 6 months. We can talk about that. But takeaway, a very simple statement. And this is important when we talk about tiers. Performance compliance. You have met the requirements of the code when your proposed design uses the same or less energy than the prescriptive reference building. Okay? So that's a geometrically identical building, one built to the prescriptive maximums, that's your reference. One is what you're actually going to build, your systems, your specs, your windows, your everything. As long as you can show you've used less energy, that's compliance. This tracks a whole bunch of stuff. A good energy model, and again, when we talk about the compliance of this, we talk about the salient features of a good energy model. We don't have the time for that today, but just be aware it does take a lot of addition, to be very frank, of energy flows in building. Which brings us to part 10, the tiered energy codes. So let's back up for a moment. I will, again, if I ask people to put a pin in it, put a pin in how we define compliance with a performance model. The proposed building uses less than or the same amount of energy as a reference. That's it. So tiered energy codes, again, talk about where we are today and where we want to be in the future. So it sets out all the requirements for compliance in the future, and then the individual provinces can set the tier of which they expect the performance data. And I think that really addresses these two things well. It's scalable in the sense that higher tiers is higher energy performance. And more importantly, it gives me a way to measure them. Because again, one of the real strengths of a tiered code is the ability to measure and compare apples to apples energy improvements in buildings. So what does it include? What's in scope, what's out of scope? First thing, tiered codes, like the rest of performance compliance, only deal with operational energy. Energy that is consumed in the use of a building. Not the energy that went into its manufacture, not the embodied energy that went into the parts, just the energy that is used in the building operations. It does not, get that second, it does not talk about the carbon content of that. Energy is energy. That is going to change. The next iteration of the code, the reason, if you recall this morning, they've renamed the standing committees at the federal level. The reason they are now on climate change is because the next iteration of the energy codes also talks about operational carbon. So now energy source starts to matter. The one after that talks about embodied carbon. That's when it's going to be a wild. If you want to be very wealthy in 10 years, get good at figuring out the mechanics between trading off operational energy for operational carbon to embodied carbon. Because as I said to my colleagues at the committee level, we have just taken a code that people struggled with the algebra part of it when it was just energy efficiency. If I'm talking about embodied and operational carbon, it's a calculus problem. Time matters now. If I build a hospital with a 100-year lifespan, the carbon equations for that project are entirely different than a wood frame building with a 25-year lifespan, which are 100% different than a 5-year temporary structure. Right now, energy code doesn't care. Building is a building is a building. In the calculus world of carbon emissions, I have every right to say I'm going to trade off operational efficiencies, recouping capital cost, may I add, because I expect this thing to be decommissioned in 5 years. And now it brings the whole question of all the material standards in the code, all of the ways you do the calculations, all of the future and present grid changes. That's a lot of rationale. And I have a sneaking suspicion if you're good at it, you can happily charge somebody $350 an hour to save them $5 million on that. That's my guess. Actually, well, back to reality. It doesn't deal with EVs or renewable energies. And it doesn't talk about sustainability objectives. So if you talk about ecological preservation, that's one quote, but that's not me. So let's just talk right now. We'll end it on this. Tiered compliance. There is only one way to comply in a tiered energy code world presently in any city. And it's literally energy production. So I think it's do we put the, nope. So we have, there's an actual table in part 10, but it is simply this. Tier 1, that's what Alberta is. I can use up to 100% of the energy of the reference. Okay? That's exactly the same criteria for Part 8 today. If we go to Tier 2, or when we go to Tier 2, it's simple. I can only use 75% of the reference. Tier 3, 50%. Tier 4, 40%. And at 40%, we kind of tummy rub engineered and said that's basically net zero energy ready. That's it. So what is the beauty of this in terms of compliance with the tiered code versus standard compliance today? One additional calculation. That is literally it. You have to give me the percentage reduction. Modeling's the same, process is the same, rules are the same, the guts of everything about it's the same. On that, I give full credit to colleagues in the Code Writing Commission. That is the right way to implement. is you just get to keep the same processes, same. So that's the entirety of how you comply with tiered energy codes. I don't know how we're doing for time, but Singh, did you want to walk them through the next couple questions?